hot or cold, in the form of a simple magnet or the spectacular aurora. What is the essential nature of magnetism? The equation for the force between magnetic poles resembles the equation for the force between electric charges, or the force between gravitational masses. Like electric charges, magnetic poles come in two kinds, called north and south. Opposite poles attract, and like poles repel. Unlike electric charges, magnetic poles always come in equal and opposite pairs. If you try to cut a magnet in two, to separate the two poles, the cut-end points create their own poles. So each fragment still has a north and a south pole. And it's just that difference between electric charges and magnetic poles that lead us to the question, can a single magnetic pole exist all by itself anywhere in the cosmos? According to certain theories, it can. Theoretically, some single magnetic poles, called magnetic monopoles, do exist. And they have existed ever since and as a result of the Big Bang. But if magnetic monopoles came into being then, where in the world are they now? A number of scientists have been searching for magnetic monopoles, but none have been found as yet. In the meantime, there are still plenty of magnetic dipoles to go around. Magnetic dipoles are two poles forever bound together into a single magnet. And they go all the way back to William Gilbert.
William Gilbert, the man who founded the study of magnetism, characterized the Earth as a giant magnet. The Earth does have an intrinsic magnetic field, and it very much is that of a giant magnet. The Earth's magnetic lines of force leave the surface in one hemisphere and return in another hemisphere, and the pattern of those lines of force is very similar to that of a bar magnet.
The magnetic field of a magnet, with its two poles, is similar in form to the electric field of two equal and opposite charges. A circular loop of electric current also creates a magnetic field of this form. And so does every proton, every neutron, and every electron in the universe. And the Earth itself has a dipole field that happens to point south, which is why compass needles on Earth point north. That point can be very useful at times, especially at a time like this. These Marines are using a compass to find their way back to camp. Soldiers as well as sailors have long used the compass to get themselves from here to there, over a hillside, or around the world. And to the extent they've succeeded, it's been because the magnetic needle of a compass always points north. But how does a compass work? Or in other words, what actually happens to a magnet in a magnetic field? In any magnetic field, a magnet experiences equal and opposite forces at its poles, so that it tends to line up with the field. In other words, the field exerts a torque that tends to make the North Pole point in the direction of the field. In fact, that's how the direction of the field is defined.
think that's one over there.
No matter the destination, the magnetic needle of a compass can point the way because it lines up with the field of the Earth.
Yeah. But if according to the map, that's...
At least it does so here on the surface.
94.
But what happens farther afield, above the surface of the Earth?
That's great.
In fact, how far does the Earth's magnetic field extend?
About 52 degrees magnetic.
Originally, people thought that the Earth's dipole field extended indefinitely into space. But now we know that that's not the case, that it's actually confined in the solar direction by the wind, the solar wind from the sun that impinges on it continuously. And it confines it to a distance of, on the order of 40,000 kilometers in the solar direction. And in the opposite direction, in the tail direction, it extends for millions of kilometers as far as we know.